Hi everyone, in this video I'm going to show you how to construct a third order Taylor polynomial for the function f of x equals the square root of x, and we are going to center this Taylor polynomial at x equals 1. So remember, to get started, when you're constructing a Taylor polynomial, what you're trying to do is create a polynomial, so we're going to call it t, of order 3, and you're going to create a polynomial. Order 3 means degree 3, so we're going to have coefficients a naught plus a sub 1. And since we're centering it at 1, we need to make sure and do a horizontal shift from 0, right 1 unit. So think of these in terms of transformations. We need our second degree term is going to be a sub 2 x minus 1 to the second power, and our last term is going to be a sub 3 times the quantity x minus 1 to the third power. So this is kind of a template for what we're going for. And when you're doing Taylor polynomials, you always need to remember that you're looking for these coefficients. And hopefully you've derived the formula for the coefficients. If not, that's a different video, but I'm just going to write it down. Our coefficients, so a sub n is always the nth derivative at wherever you're centered. In this case, we're centering at 1, all over n factorial. So as we kind of go through the process, we want to keep this in mind and remember that this is how we get our coefficients. All right, so let's go ahead and get started. We are starting with our function f of x equals the square root of x, and we are going to evaluate the first 3 derivatives at 1 so that we can use this formula. So my first derivative is 1/2 x to the negative 1/2. My second derivative is negative 1/4 x to the negative 3/2. And my third derivative is positive 3/8 x to the negative 5/2. I'm going to evaluate each one of these where we want to center the Taylor polynomial. Since we're centering it at 1, we're going to evaluate each one of these at 1. So evaluate at 1, evaluate at 1, evaluate at 1. Okay, when we evaluate this at 1, we are going to get 1. F prime evaluated at 1 is going to be 1/2. F double prime evaluated at 1 is negative 1/4. And the third derivative evaluated at 1 is 3/8. It's kind of nice that we're evaluating at 1 because it doesn't matter what the exponent is. That x to whatever exponent will always be 1. So we get a little lucky there. Okay, now we need to build our coefficients. So a naught is going to equal our first function evaluated at 1. So that's going to be 1 divided by 0 factorial, which is 1. A sub 1 is going to be our derivative evaluated at 1, 1/2 divided by 1 factorial, which is 1/2. A sub 2 is going to be negative 1/4 divided by 2 factorial, which is negative 1/8. And a sub 3 is going to be 3/8 divided by 3 factorial, which is 3/8 times 1 over 3 times 2, which is 1/16. Okay, now that we have these coefficients, we can plug them in to our Taylor polynomial and write our polynomial. So our final polynomial will be our third degree Taylor polynomial for x centered at 1 is going to be 1 plus 1/2 x minus 1 minus 1/8 x minus 1 quantity squared plus 1/16 x minus 1 cubed. The last thing I want to show you is how this graphically compares to my original function f of x, because that's kind of the whole point of building the Taylor polynomial. Okay, if we look at the graph of our function, this is f of x equals the square root of x. As I build my Taylor polynomial, you're going to see how my Taylor polynomials begin to match my graph. So this is my Taylor polynomial, whoops, sorry about that, of degree 0. This is just t equals 1. You can see at 1, these two are exactly the same. So when we center a Taylor polynomial at a value, it's going to be perfect at that particular value no matter what the degree. If I make a Taylor polynomial of degree 1, now that blue function matches the red original function much better than the green t equals 1 line. As we continue, I'm going to turn off our degree 0. This is our second degree. That one's even better. And our third degree is right here. And that one looks really good. Okay, in fact, it matches that function very well, even plus or minus 1/2 from our center. Okay, so that's kind of the whole purpose of building a Taylor polynomial. We want to build a polynomial that matches a function, and we want to center it at some particular value. I hope this makes a lot more sense. Hope your understanding of Taylor polynomials is much deeper now.